Hello and welcome to this session on AutoEncoders. Now, AutoEncoders is a very important architecture in deep learning, and our use of AutoEncoder throughout this section really falls a lot more under unsupervised learning rather than a supervised learning. Recall that previously throughout the ANN section, recurrent neural network and convolutional neural networks, we were dealing with historical data that were already labeled for us. We already knew what, for instance, the image label was, whether it was a dog or cat, or whether it was whether it was a cancerous benign tumor. So when we are dealing with autoencoders, our use case for them really falls under unsupervised learning. So I really want to review what applications we are going to be using autoencoders for and why it is labeled as unsupervised learning instead of supervised learning. So we are going to be using autoencoders for two main things. One is dimensional reduction, which is pretty much what all autoencoders do to some degree. And then we'll see how we can use this dimensional reduction to actually remove the noise from images. So during the training of certain models, we actually sometimes get access to historical data with correct labels. However, during the actual use of the model, we won't be able to use our previous evaluation matrix, and that will make a lot more sense when we actually see how we construct these models and we how we actually use them in a real world situation. So recall that unsupervised learning means we don't have those correct labels to compare our results to. And I should mention that our use case for autoencoders are actually sometimes called semi-supervised. So it is not completely unsupervised, but it is definitely not completely supervised either. So sometimes people like to call this as semi-supervised. Now, the reason they use this term semi supervised is because while we are actually training the autoencoders, we do take advantage of having sometimes historical labels. However, when we are actually using this autoencoder, we don't really have a situation where we can produce some sort of nice classification report and some sort of maybe root mean square error or accuracy. And that will make a lot more sense when we see the use cases of dimension reduction or noise removal. So to fully understand this, we have to first understand what autoencoder is and how it actually works. Autoencoders is actually a very simple neural network and will feel very similar to the multi-layer perceptron models that we built during the artificial neural network section. And the main idea is that an autoencoder is designed to simply reproduce its input at the output layer. So that means the key difference between an autoencoder and the typical MLP network is that the number of neurons is equal to the number of neurons at input is equal to the number of neurons at output. Typically in our use case we have been either having the output be equal to certain number of classes that we are classifying for, or equal to one neuron if you are dealing with the continuous output. However, in kind of a strange case here for the autoencoder, the number of input neurons is exactly equal to the number of output neuron. So let us explore what this actually looks like and why would we would want to be able to build a network this way. So here we can see an example autoencoder. Notice the shape here. We start with 5 neurons and then slowly we are reducing down to a certain specified number of neuron throughout the hidden layer. So I go to maybe it's 5 to 3 to 2 1. And the main idea here is right in the middle of your autoencoder, you are going to reduce to some desired amount of neuron, essentially trying to capture what information is important. And in the second half of the autoencoder, essentially the decoding part, you expand this back out to equal to the same number of neurons that you started with. So we go from 5 to 3 to 1 and then back to 3 to 5 again. So we start at 5 and we end up at 5. That is the gist of the uh, autoencoder, and very important point that you have to take away home. Now let us walk through the layers and see the basic idea of the autoencoder. And to simplify this further, let us imagine that we have this very a simple single layered architecture. So you go to 5 to 2 to 5 back again. And the idea here is that in order to produce the same output at the final layer, that the hidden layer, or specifically the internal multiple hidden layers for a real autoencoder, for example, those hidden layers must actually learn what features are important. And this kind of extreme example basically shows you that in order for this input to be reproduced as output, those two neurons in the hidden layer, they are going to have to learn which inputs are actually important in order to reproduce the output. So they are reducing the amount of dimensions from 5 to 2. So again, we see here that we have a dimension of 5 reduced to a dimension of 2 and then expanded back to the original 5. Notice my use of the word dimensions. I'm not saying the word features here. Okay. Again, the feed forward network is trained to produce its input at the output layer. This is what all autoencoder is. We have some input that gets reduced to a hidden layer in the middle and then expanded back to the original size in the output. This is the architecture of the autoencoder. Now, output size here again same as the input size, and that hidden representation attempts to maintain the important input information before being decoded or expanded back out. And then later on, we'll see how we can actually take the advantage of that hidden layer to extract meaningful insight. So when we do things like dimension reduction, we'll be actually be able to train a full autoencoder and then split it in half and directly extract results from the middle hidden layer. But the full autoencoder is actually inputs shrunken down to hidden and then expanded back out to output. So this idea is actually extremely similar to principal component analysis in statistical machine learning models. We are trying to reduce, I'm sorry, classical machine learning models. Here we are trying to reduce the dimension reduction we are trying to reduce the dimensions into a fewer principal component. And keep in mind that we can explore stacked autoencoders with more hidden layers, and we'll actually be doing this ourselves throughout the Jupyter notebook or Google Colab shortly. Now, a really important note here: a lot of uh, learners, they get confused by this term reduction in dimensionality. Keep in mind that those hidden layers, they are not simply subselection of only certain feature. So it's not like that you start off with 10 feature and then you choose 8 of those 10 feature to continue on with. What you are actually doing here is you are calculating the combination of the original feature to represent the original dimension in a reduced dimensional space. So again, you're not sub-selecting feature, you are actually taking a little bit of all the features, some percent depending on the way the auto encoder is trained. So for example, you may take my maybe 5% of feature 1, maybe 10% of feature 2, and etc. And you decide how important is each feature as you slowly reduce this dimension down. And then that hopefully that hidden layer in the middle is going to learn which features are the most important and how to organize them in a way to reduce the dimensionality. And then again, to check if it is working or not, we decode or expand this back to the output layer. So again, we are not sub-selecting only certain features. So what does it look like in practice? Well, later on, we'll see that we are going to explore how we can actually use an autoencoder and split it into two parts, and a encoder and a decoder to perform dimension reduction. So we'll be able to actually take a three-dimensional data set and then reduce it down to either two or even one dimension. So notice here that we have two cluster, and we are able to map them to a lower dimensional space and still maintain this separation. So in this particular use case of going down from 3 to 2, that may not look actually very useful to you. However, you can imagine that if you are dealing with a data set that are much larger than just three feature, so if you have a data set maybe about of maybe 30 feature or 40 feature, something very large, you cannot just visualize those 30 feature in three-dimensional space because we are living in a 3D world. So to visualize them or to see the get some visual idea of those feature, what we'll do is we will reduce the dimension using this technique and put it back to maybe 3 dimension or 4 dimension, then just plot it out, right? So as we reduce this down dimension, right, dimensionality wise, you can imagine that if you are start off with a very high dimension data set that was too highly dimensional to visualize, we could reduce this down to 3D to or 2D, and then visualize the classes and see just how separable our data set is. And then later on, we'll see how we can apply this to just reveal hidden insights from our data. Again, the main idea behind an autoencoder is the center hidden layer, reduce the dimensionality to learn the most important combinations of original feature. And we are going to see two applications of the autoencoder. They both use an autoencoder here, but they use them in very different ways, which is why this is such an interesting network architecture, because even though you have the same network architecture of inputs being reduced and then matching the output size, you can use them in a variety of tasks. So again, we'll be exploring two use cases. One is the more obvious one, that is the use case of dimension reduction, where you essentially, after training an autoencoder, split it in half and just extract the hidden layer output. And then the second use case is a really interesting one for the noise removal. You will actually have that hidden layer essentially learn how to filter out noise when reproducing the output. So both of these uh, use autoencoder, but they use them in a different manner. They are super interesting problem sets. So what we are going to do is we are going to first explore the first one, that is autoencoders for the dimension reduction, and then we'll talk about the noise removal. Let us talk about dimension reduction before we go to the coding part. So we can use an autoencoder for dimension reduction by separating out the autoencoders into two parts, the encoder and the decoder. Now, here we have the full autoencoder. Recall the autoencoder, the main idea here is that we have the same number of input as we do output, and then inside of the autoencoder we do a dimension reduction and then expand this back out to the original dimensions. So what we end up doing is we separate this out into two parts, an encoder and a decoder, where the idea of the encoder is to take something that is highly dimensional and then encode it into a lower dimensional space. And basically the decoder's job is to expand back out that low dimensionality in order to make sure that hidden layer in the middle of the autoencoder is actually learning correctly what features are important. Because if it is not able to learn correctly what combination of feature is important, then you're going to have a really poor output. That is the job of the decoder. So what we do is we train this all together until the hidden layer becomes really good at extracting useful information, and then a decoder can expand that back out. Once we have trained the full autoencoder, then just grab the encoder section. And now we have something that successfully reduced the dimensionality. So we train them together, but when we actually want to use them, we will only grab the encoder part. So this encoder can now successfully reduce the dimensionality of the original data by taking the combination of the original feature and, well, you may be asking what use case does this have? Again, I've already I've already explained this, but dimension reduction, and I'll repeat myself that dimension reduction has a wide variety of use cases. It can be used for things like compressing your data set, visualizing data in lower dimensions, and most importantly, revealing hidden relationships that are not basically clearly seen unless you plot them out obviously, right? So when you're dealing with feature data that goes beyond three dimension, then it becomes difficult to actually visualize this and understand the relationship, especially if you're performing something like a classification task. So it may be quite useful to understand just how separated are these classes. And if you're able to visualize this either in 3D or 2D, you may be able to get an understanding of just how separable these classes are. So, for example, here we have an example of dimension reduction. We are starting from three dimensions again, and we can see we have two clusters that are highly separable, and we are able to actually visualize three dimension. But you can imagine that this could have been 11 dimension, or maybe 41 dimension, or maybe 100 dimension, where there is no way to visualize the classes themselves. So in that case, you would reduce the dimension to maybe two dimension or three dimension, and then just plot them out. Now, let us actually code this out exact problem set. And for that, I'll hop back to the Google Colab.